So our aim of the experiment is X-ray powder diffraction 2. And in this experiment, what we are going to do is that we have got this intensity versus 2 theta plot. And from that, we have to find out the intensities theoretically and match with the observed one. Okay. So in previous experiment, we did Miller indices in peak indexing for this same plot, and we know the values, and this sample belongs to cubic system. So that is what we know. And sodium chloride, so FCC structure that we are also aware of. This 2 theta value, intensity, and HKL are now known to us. Now we have to understand the intensity values which we are getting and compare them with the theoretical. Okay. So to do that, we required certain things, and the procedure is shown here. Okay. So in this procedure, what we are supposed to do is that there are certain theoretical part. So the factors affecting the relative intensity of any diffraction lines of a XRD pattern are given by atomic scattering factor F, which is known for every elements. Structure factor capital F depends on the unit cell and the atomic scattering factor. Multiplicity factor P is there. So, and Lorentz polarization factor given by 1 plus cos square 2 theta sin square theta cos theta. Okay. So all these club together to get I calculated. This is calculated intensity, which is equal to mod of F square into P bracket 1 plus cos square 2 theta upon sin square theta cos 2 theta. Okay. So this is a small theory to calculate the intensity of the XRD peaks that we are getting, and then matching the theoretical one. So to do so, what we are supposed to do is this. Okay. So there is a multiplicity factor that we saw earlier. Okay. Multiplicity factor for this kind of system is given by which is depends on the HKL values of the particular XRD pattern. So this is HKL values 111, 200, 220, 222, 400, 420 for the corresponding 2 theta values. So for each 2 theta values, you have to tabulate this multiplication factor by looking at the HKL values. So when HKL are separate, all three are different, then you have to take 48 as a multiplication factor. When two of the values are same, HHL, then you have to take it as a 24. So say 221, 113 kind of thing. Okay. When one of the factor is 0 and other two are different, then you have to take 24. Okay. Like 420 here. So one is 0 and then this is different. Then you have a 0 kk. Okay. So this is 0, not O. 0 kk, then you have to take 12. So you have here a 220, which is similar to this. So you will take 12. Then all three are same, H. Then you have to use 8. And two of the Miller indices are 0. Then you have to use 6. Okay. So 200, 400 will take multiplication factor 6. So this way you have to add one more column here. Okay. So 2 theta, you have got intensity. You can make it theta value, or you can put HKL value here, and then you can take theta, then sin square theta, and all this calculation part. Okay. Then comes the second part. Since this is salt, which is made up of two different elements, sodium and chlorine. So therefore, what we do is that we take sample B and sample C values. Okay, these values and sine theta upon lambda strong inverse. For this particular value 0.0, 0.0, 0.1, you have to plot the graph. So on y-axis, you will put sample B, sample C parameters, and on x-axis, you will put this, and you will plot the graph which is shown here. So you have to plot the graph like so. Here you have sine theta upon lambda values. Here you have the values which are represented in this table for two different elements. After that, manually draw like this, and then you have to proceed for the next calculation. So then in next process, what you are supposed to do, once you do the calculation, certain things are tabulated here. For sample A means it is purely made up of single element. So if you take silicon or any metal, iron, copper, something like that, which is having FCC structure, then you will go with the table of A, sine theta by lambda and sample A. You will plot this graph, and there is only one element. If there are two elements, then you will go with B and C. That is what for this cubic structure. So we will not. So if you have silicon, then you will mod of F square equal to 0 for mixed indices. Okay. And mod of F square equal to 16 F square for unmixed index. This is sample B, NaCl. So the multiplication factor, atomic scattering factor, F mod of F square is given by, or F square is 16 Fy plus Fz whole square if H plus K plus L is equal to even value. Okay. So here H plus K plus L, which is 1, 1, 1, then it is 3. So this is odd. But this is 2, 0, 0. So 2 plus 0 plus 0 actually is 2. So then you can use it, this value. So as per this, H plus K plus L even and odd. So don't look this table. So instead of this, you will get simply this is 3 only. This is actually 2. This is going to be 4. And this will be 6. And this is 4. Okay. So you are having H plus K plus L equal to 4 even values. And only for one case you have odd in this particular thing. So 16 Fy minus Fz whole square. Fy belongs to sodium and this belongs to chlorine. Okay. Sodium, chlorine, multiplicity factor P that I already told you, depending upon the HKL values, 8, 6, 16. Okay. So 1, 1, 1, 2, 0, 0, like this. This is going to this values. Then F1 and F2 that you have to find out from the graph. So how you are going to find out? Here it is already calculated. For this given value of 2 theta, you will take theta value sine theta, divided that by 1.54, which is the wavelength of our copper X-ray source. Okay. So once you divide it by copper wavelength, then you will get this 0.150, 0.172 and all these things. So these values are not matching exactly with the values shown here. This is 0.0, 0.1, 0.2 like this. So the first value is between 0.1 to 0.2. So now on this graph, you have to go to the 0.15 and come here. This is the intersection point for sodium, the lower one. Then further extend it to the next curve, and this is going to be a chlorine part. Okay. So these two values you have to take it from this graph, this curve. Okay. So do it for all 2 theta values or theta values, sine theta by lambda. Okay. So once you do it, you will be able to tabulate this thing. For sodium 8.9, 13.1. Okay. This corresponds to this value 0.15, then 0.172, 8.6 and 12.5. Then for 0.248, you are going to get 7.4 and 10.5. Okay, so everything is from the given parameters. Okay, so you need not to go and search anything. All the things, necessary things are provided. Okay, so after that you calculate 1 plus cos square 2 theta upon sin square theta cos theta. So you can tabulate these values, cos square 2 theta, sin square theta, cos theta, if you want, for the simplicity. And then in this particular column you can calculate. So you have got f1, f2. Now one more column you will have to add for this part, mod of f square. Okay, so f square is this 16 fy plus fz. Then you have to again check this value is even or odd. Okay, once you check these values, after that you will be able to get mod of f square value. Okay, as per the formula that we saw here, mod of f square. Now you have got p value. Okay, p value is simply on the HKL parameter, but this multiplicity, atomic scattering factor, then HKL dependent factor, and this value. So three value once you calculate, then you will get the final intensity like this. Okay, so after getting these intensities at individual peak, you have to normalize the intensities. So take the maximum peak intensity and divide the take it in the denominator and divide all the intensities and then multiply with 100. So what will happen? This is going to give you 100% intensity. Then you are getting 64%. So this is normalized calculated intensity. Repeat the procedure for the observed one. So observed intensities are given, or you can so these intensities are already given. If these are not given, you can take a scale, measure the height, okay, and see the scale. This scale means you can take a ruler and note down the length of this peak, okay, and then you know you have this for say scale for 1 centimeter equal to 2. So multiply with that height. That will give you the intensity. Okay, so repeat it for the various peaks, and then you are going to get this thing. So once you get all these things observed, again you normalize. So after doing this, then you can tabulate, say peak number 1, 2, 3, 4, 2 theta or theta value corresponding HKL if you want to put it. That will be better. Then you can put normalized, observed, and calculated values. Okay, since we have all these records, so we can normalize to a standard scale and then put it, and then you can just comment on the nature of the peak. So for the 100%, you have a very strong, then 64%. So the way you have a grading, O grade, A grade, B grade. So scale it on that particular percentage pattern, and then you can say certain peaks are very weak. The intensity is very low. So maybe 35% or 40% below that, you can say weak, or 20%, below 20%, you may have weak intensities and all these things. Okay, so this is part of your comment. Then the question may come that why certain peaks are on calculation shows very strong intensity, but when you observe, then they are not showing the similar intensities. Okay, so here from the calculation and the observation, we see both are 100%. This particular position, peak position, is very strong. Okay, similarly in this case, this is the second highest peak, 59-64%. So they are comparable. But then certain cases, sometimes this happens that from calculation you may get some 64% peak, and here you will get from observation you may get very low response, very weak peak, 8% or 7%. So in that case, you will have to think about the theory and the observation. Okay, so that will be the question.